Hi, guys. My daughter has been sick this weekend, so I am staying at home with her today. But I wanted to make sure we got the notes together. So your sub should be passing out the Chapter 5 packets. Next time, I will put you in your new groups for the group project, and we'll assign AP problems for that and go over what we're doing with that. But today, we're just going to talk about 5.1, which is the start of integrals. So let me go ahead and share my screen. Switch cameras rather. Okay, so we're going to start in 5.1 talking about antiderivatives and indefinite integration. So an antiderivative or an integral is quite literally the opposite or the undoing of derivatives. So we have this function 3x squared, and we want to find the antiderivative. So I want to undo what the derivative did. So a derivative, if I took the derivative of x to the n, I would move that n down in front and then have x to the n minus 1. When I'm taking the antiderivative or the integral, I kind of work the opposite way. Instead of having x minus 1, I'm going to add 1 to my power and then multiply by the reciprocal of my new power in front. Okay? So with 3x squared, I'm going to have my new power be a cube because I add 1 to my power. The 3 stays, and then I'm going to multiply by the reciprocal of my power, of my new power, which is a 3. So 1/3. Obviously, that 1/3 and the 3 cancel out, and I have x cubed. Now, this is just an antiderivative, not the antiderivative, because I could have lots of different options for this. For example, look at the second one. If I want to take the antiderivative of 4x cubed, again, I'm going to add 1 to my power, so x to the 4th, keep the 4 that was there, and then the reciprocal of 1 over my new power, 1/4. Those 4's cancel, so I should have x to the 4th. Okay, and if I took the derivative of x to the 4th, I would get this 4x cubed. Okay, so that's how I check that it is an antiderivative. But what if I took the derivative of 4x or x to the 4th plus 5? I would still get 4x cubed. And if I took x to the 4th minus 2, I would still get 4x cubed. So all of these are different antiderivatives. So if we don't have an initial condition or limits of integration, we're going to always put a plus c, which is a constant of integration, at the end of our statement. So really, instead of x to the 4th by itself, I should have that plus c sitting there. Okay, so the operation of finding the antiderivative is called indefinite integration. Okay, and this is what our statement will look like. This is an integral sign. This is what we call the integrand. Sorry, there's some trick-or-treaters here. Okay, so if we take the integral of a derivative, we should get back our original function. This dx, just kind of like in taking a derivative, tells us what variable we're taking the integral with respect to. So we'll call it the variable of integration. And then our answer, we'll get that f of x back since we took the integral of a derivative. And of course, we're adding our plus c to it, which is that constant of integration. So just like in derivatives, we're going to have some basic integration rules. I'm going to start with k dx. So there's no x just sitting here that we can see. But think of it as having like kx to the 0th. Well, if I add 1 to that power, now I'm going to have kx. So my integral will be kx plus c. With the 0, the same thing is happening, except for that k is 0. So I'm going to have 0x plus c, or just c. Okay. Now, if I have a constant times a function, so k times f prime of x, I can actually take that k outside the integral sign and just take the integral of f prime of x dx, which will give us k f of x plus c. Just like in derivatives, I can add or subtract my integrand, and that will give me f of x plus or minus g of x. And then we also already talked about this power rule per se, where we have x to the n plus 1 now over n plus 1, or times our reciprocal of our new power. Okay, so that's kind of like our power rule. That is like the only, power rule is the only thing that derivatives and integrals kind of share. And again, it's different for derivatives than it is with integrals. We will not do product rule or quotient rule or chain rule when we're taking the integral. Those are things that apply solely to derivatives. In chapter 8, we talk about some more advanced integration techniques that kind of combat chain rule. But again, we'll get to that later. For right now, let's try some practice. So this first one, we have 3x dx. We can take the 3 outside the integral if we choose to do that. Right now, our x has a power of 1. Okay, so if I want to add to that, I'm going to have x squared 1 over the new power, so 1/2, and then I have that 3. So that's what's sitting out in front. So my answer is going to be 3/2 x squared plus c. This next one, I have 1 over x squared. Just like with integrals, I may want to just like with derivatives, I may want to rewrite my integrals. So I can rewrite 1 over x squared as x to the -2. Okay. When I add 1 to my power, I now have x to the -1. And then I divide by my new power and multiply by the reciprocal. Add my plus c. So my final answer is going to be -1 over x plus c. Now, it is really important to note that if I have the integral of x to the -1, that is not x to the 0th, okay? If I have the x to the -1 is the same as 1 over x, okay? We knew with derivatives, if we took the derivative of ln x, we got 1 over x. And since integrals and derivatives are inverse operations, if I have the integral of 1 over x, I'm going to get ln x. Okay? And this is important to remember. It will come up a lot in the spring when we do different integrations and things that kind of trick out to this solution. So if you see 1 over x or x to the -1, do not put x to the 0. We need to have it as ln x. Okay. Our third example, we have radical t. So we can rewrite this as t to the 1/2 dt. Again, I add 1 to my power. So I have t to the 3/2, and I multiply by the reciprocal of my new power. And there's our answer. When we have something like this in 4y plus 2, we can take the integral of each part, one part at a time. So the integral of y, is 1/2 y squared. I've added 1 to my power and then move the reciprocal of the power in front. And then the integral of 2, remember I need to add my variable in there. So 2y and then plus c. The same that is true down here on 5, just one piece at a time. So 2 theta squared, I'm going to have theta cubed. The 2 stays and I divide by 3 because that's my new power. Minus 3 theta, we're going to move that to theta squared. The 3 stays, divide by my new power. Plus 1 becomes plus theta, and then plus c. Six is perhaps the trickiest on this page because we're used to seeing this and thinking, oh, we need to do quotient rule, but that's derivatives, remember? Quotient rule does not happen with integrals. So I need to look at this in a different way. And with that, I see that it is sitting over a common denominator. Okay, I only have one denominator. It is a common denominator. So I can split my numerator. I can write this as the integral of x over radical x plus 1 over radical x. Okay. And again, I can adjust my powers. This is x to the first over x to the 1/2. If I subtract down with my powers, I'm going to be left with x to the 1/2. And then this is already in the denominator, so that's x to the negative 1/2. Okay, now this is a lot easier to take the integral of than what we started with. I'm going to add a power. So that'll be x to the 3/2 and then times 2/3. If I add 1 to negative 1/2, that becomes positive 1/2 multiplied by the reciprocal of my new power. So times 2. And then don't forget your plus c at the end. Okay. Just like in derivatives, we also want to talk about trig. These were your 6 trig derivatives that I told you to memorize. If you know them, you will have no problem with your trig integrals. Again, there are 6 trig integrals that you need to memorize. Okay. The derivative of sine is cosine. So when we take the integral of cosine, we are going to get back sine. Derivative of cosine was negative sine. If I take the integral of sine, I'm going to get negative cosine. Derivative of tangent was secant squared. Integral of secant squared is going to be tangent. Derivative of cotangent was negative cosecant squared. Integral of cosecant squared is going to be negative cotangent. Derivative of secant is going to be secant tangent. Integral of secant tangent is secant. Derivative of cosecant is negative cosecant cotangent. Integral of cosecant cotangent is negative cosecant. Okay, again, these are the 6 you need to memorize. If you were ever asked for the integral of just plain old secant or something like that, that is not one of these 6, there is a way to do it. It's very complex. It involves the natural log. It is on the formula sheet, like the 2nd page in your binder. I will not ask you one of those on a test or a quiz without having the formula sheet with you, because that's really unfair. These 6, though, are fair game. And with derivatives, a lot of times we just saw sine and cosine. With integrals, you'll see more of these other ones as well. I know we use secant tangent quite a bit, secant squared. So those will come up. So it is important that we do memorize these. We'll go ahead and play with some of the examples that use our trig. And not only do these use the trig integrals that we just talked about, these also use trig identities that you did in pre-cal. So sine x over cosine squared x, again, we're not using a quotient rule, so we need to figure out a way to kind of break this down. So I could rewrite this. I have two cosines in the denominator, so I could rewrite it as sine x over cosine x times 1 over cosine x. Well, I know sine over cosine is tangent. 1 over cosine is secant. And I know what the integral of secant tangent is. This is the same, multiplication is commutative. So I know my answer here should be secant x plus c. Okay. This next one, again, on my list of those 6, I do not have cotangent sine, but we know that that cotangent is cosine over sine. Okay, so once I've translated cotangent with an identity, I see that these signs are going to cancel out, and I'll have the integral of cosine x dx. The integral of cosine is sine x plus c. These ones are a little bit easier because they look complex, but they're not. I can take the integral of each part because I know each part from that list of those 6 integrals. So if I'm looking at secant squared x, the integral of secant squared x is tangent x. The integral of sine x is negative cosine x. The integral of negative cosecant is going to be positive cotangent. Okay, because we saw on the front that positive cosecant was negative cotangent. Here we had negative cosecant squared, so we'll have positive cotangent. Those signs do flip. And then plus c. And this last one, the first thing I probably want to do is to distribute this negative. So we'll have the integral of negative secant tangent plus cosine. Well, we know secant tangent is secant. So if I have a negative I have a negative secant tangent, I will have a negative secant. And then the integral of cosine is sine. And then, of course, our plus c. Okay. The last thing we want to talk about for 5.1 is particular solutions. Okay, so this is kind of starting to solve a little bit more to kind of get rid of that plus c value that we have. So they will give us something that has an initial condition. Sorry, more trick-or-treaters. So we can solve a little bit further and get rid of that plus c. So they tell us that we need to find the particular solution that satisfies this initial condition when f is 1, when x is 1, y is 0. For the derivative f prime of x is 1 over x squared, where x is greater than 0. So we are given this f prime of x part. If we want to get to f of x, we're going to need to take the integral. So I'm going to set up my problem like that to start. Again, I can rewrite this integral to be x to the negative 2 instead. Okay, when I add one to, I'm taking the integral and add 1 to the power, I'll have x to the negative 1 over negative 1, or negative 1 over x plus c. Okay, so that's f of x. Then we can use our initial condition and plug in. So we know when x is 1, y is 0. So c must be 1. So my f of x is negative 1 over x plus 1. Okay, and we're going to do another one to kind of practice that, because we can go through this step or these process of steps a couple different times. So our next one says we're given a second derivative, 2x plus 3, and we have now two initial conditions, one for the derivative and one for the original function. Okay, so to take the second derivative, the integral of that, we will get back the first derivative. Okay, and that's when we can use that first initial condition that goes with the first derivative. So we will take the integral of 2x plus 3 adding 1 to my power is x squared times the 1/2 will cancel out with that 2. And then the integral of 3 will be 3x. And then plus c. So this is f prime of x. And we're going to use our initial condition when x is 2, y is 8. Okay, so this is 4 plus 6 plus c. It's 10. Subtract that over. C is negative 2. So we know that f prime of x is x squared plus 3x minus 2. Again, we want to get down to f of x, so we're going to take the integral of this. If I add 1 to my power, I'm going to have x cubed times the 1/3 in front. I'm adding 1 to this power, that's a 2 times the reciprocal of 1/2 and then 3 there, minus 2x plus c. And now I can use my second initial condition that says when f is 2, y is 0. Okay, so if you want to label these as different c's, we can. This is our first c that we found. This is going to be our second c. And the second c, if we calculate this out, will be negative 14 over 3. So my f of x, write this around the side here, I'm out of room, is going to be, 1/3 x cubed plus 3/2 x squared minus 2x minus 14/3. That is my entire f of x equation. Okay. The last problem we'll do is this word problem. They give you the picture of what this graph kind of looks like. So we can kind of check our answer, but we do want to make sure we're doing this with our calculus skills. They are telling us a ball is thrown upward with an initial velocity of 64 feet. Okay. and an initial height of 80 feet. We want to find the position function. So we know position is the antiderivative of velocity, because velocity is the derivative of position, as a function of time t. So this is saying that when t is 0, our initial time, our initial velocity is 64. And the initial height is saying that when our position, r of t, r of 0, because it's the initial, we start at 80 feet. Okay, and our graph does show that our initial position should be 80. Okay, and time is 0, that is 80. So we want to find our position first. Then we're going to find when the ball hits the ground. Then we're going to find the velocity when it hits the ground. And the last thing they tell us is that the acceleration is -32. Okay, so where do we get started with this? We have initial velocity, we have initial height. We know that height is going to come from the integral of velocity, but we don't even have an equation for velocity. Okay, but what we do have is an equation for acceleration. And we know that the derivative of velocity is acceleration. So if we took the integral of acceleration, we will end up with velocity. Okay, so if I take the integral of -32t, I'm going to have -32t plus c. I'm going to use my initial velocity condition. So when t is 0, velocity is 64. That means that c, this first c, is 64. So my velocity equation is -32t plus 64. Okay, they asked us to find position. So we're going to take the integral of velocity. That will give us our position r of t. Okay, if I take my derivative, my integral, I add 1 to my power, so this is t squared, dividing by 2, because that's the reciprocal of my new power. -32 divided by 2 is -16. And then this is 64 times t, because I have to add in a t there, and then plus c. Now I can use my second initial condition that r of 0 is 80. So c must be 80. So my position equation, r of t, is -16t squared plus 64t plus 80. Okay, that is the first part of my question. Find the position. And then it asks when the ball hits the ground. Well, we can easily see from our graph that is at 5. Okay, but we want to solve it with our calculus skills. So we're going to look at our position. We know that when the ball hits the ground, its position is going to be 0. So we're going to set our function equal to 0. I'm now going to factor out a -16. That makes this inside part a lot easier to factor. Well, t minus 5, t plus 1. So t can be 5 or -1. We know time cannot be negative, so we'll leave it as t is 5. That's where it's hitting the ground. And it matches up with what our graph tells us. The last thing it asks is what is the velocity when the ball hits the ground? Okay, so we're going to go back to our velocity equation that we had here. And we know that when it hits the ground, time is 5. So we want to find v of 5. Okay, so we'll plug 5 in for t, and that's going to give us negative 96 feet per second. And we will go ahead and stop there for today. Your homework will be on WebAssign and you'll have a quiz next time over this section, over indefinite integrals. Okay, so quiz and WebAssign. And I will hopefully see you guys Wednesday.